All right, chemistry class, let's look at the chapter 15 review questions. And we're going to go through these together so you can better understand some of the concepts and maybe some of the calculations that you need to do in chapter 15. Remember, we're talking about acids and bases. Okay? Number 1 says, why is pure water a very weak electric conductor? In order for it to be an electric conductor, conduct electricity, it has to have ions in it. And pure water does have some ions. Remember, it self-ionizes. H2O and another H2O. One of these is going to donate its proton, the H plus, to the other. And you're going to have hydronium ion and hydroxide ions. Okay? The one that donated the H plus is going to turn into the hydroxide. The one that accepted the proton, the H plus, is going to turn into your hydronium. It does have ions in it, pure water, but to a very, very small extent. Remember, the product of these concentrations is going to equal that constant K sub W. The product of the two concentrations of the hydronium and the hydroxide ions is a small number. At 25 degrees Celsius, it is 10 to the negative 14. That's tiny. So that means you don't have a lot of ions. It happens, but to a very, very small extent. So it is going to be a weak electrolyte, a very weak electric conductor. Okay? Number 2 says, what does it mean when a chemical formula is enclosed in brackets? That means concentration. Okay? And probably molarity. Molarity is the moles of the solute divided by the liters of solution. Okay? So when we put something in brackets like here, it means the concentration of that ion, the concentration of hydroxide ion. Okay? Or the concentration of whatever is in brackets. All right, number 3. What is always true about the hydronium ion concentration? Do you see how I read that? Hydronium ion concentration value of acidic solutions. Well, if it's acidic, what that means is that the hydronium ion concentration has to be greater than the hydroxide ion concentration. Okay? And remember, when something is neutral, when it's neutral, both of these are going to be equal to each other, and at 25 degrees Celsius, they are going to be equal to 10 to the negative 7. So if it's acidic, that means that the hydronium ion concentration, we may not know exactly what it is, but we know it has to be greater than 10 to the negative 7. And that would force the hydronium ion concentration to be less than 10 to the negative 7. Okay? Identify each of the following solutions as acidic, basic, or neutral. All you have to do is compare the concentration to what? 10 to the negative 7. If the hydronium ion is greater than 10 to the negative 7, then the solution is going to be acidic. If the hydronium ion is less than 10 to the negative 7, it's going to be basic. Or if it's equal to 10 to the negative 7, it's going to be neutral. Here, 10 to the negative 10 is less than 10 to the negative 7, so it's going to be basic. Okay? Let's look at this one. What if they're equal? If they're equal, it is going to be neutral. Okay? What about the OH, the hydroxide ion? If hydroxide ion is greater than negative 7, 10 to the negative 7, then it's basic. You've got more hydroxide than you would hydronium. And so in this case, 10 to the negative 11 is less than 10 to the negative 7. So you've got fewer you have fewer hydroxide ion concentration than you would hydronium. So this is going to be acidic. The hydroxide ion concentration is very small, less than 10 to the negative 7. Okay? All right, what about pH? Well, pH is just a way to measure concentration also. Remember, pH is the negative log of the concentration of the hydronium ions. So if the pH is high, that means it's actually the reverse of what you think. If the pH is high, it actually means the hydronium ion concentration is low. Because, let's take this one right here. Remember this is a low number, 10 to the negative 10. If I do the negative log of 10 to the negative 10, well, forget about the negative in front for a second. The log of 10 to the negative 10 is asking you 10 to what power gives you 10 to the negative 10? Well, that answer is negative 10. And then you take the opposite of that. You see when this is a very small number, and then you take the opposite of that log, you're going to get positive 10. So if the pH is above 7, that means the concentration of hydronium ions is very small. Here it's 13, so that's going to be basic. Okay? A pH above 7 is basic. A pH below 7 is acidic. So this one here is acidic. Okay? We're not going to worry about number 5 right now, and we're not going to worry about number 6 or 7, nor are we going to do number 8 for right now. Okay? All right, we do have to be able to calculate the concentration and the pH, and I'm going to just remind you here. Well, I'll just refer to it when I go through this. I'll show you the calculations as we go. Okay? Here it says find the concentration of hydronium and hydroxide for each of the following. Now here, HCl, if you refer to the list of strong acids, this is a strong acid. So when HCl breaks apart into its ions, every one HCl is going to give you one hydronium ion. Remember, this is in water. So the H plus from the HCl, the H plus here is being added to the water to make the hydronium. So for every one HCl, you're going to get one hydronium. Well, if you've got 0.03 molar HCl, if this is 0.03, then this is going to be 0.03 as well. Done. 0.03. All right? That's it. And you know that the concentrations of the hydronium and the hydroxide multiply together to give you 10 to the negative 14. So to find the hydroxide, I take 10 to the negative 14 and I divide by 0.03. And you can do that calculation. Okay? Here we have another strong acid. So for every one HNO3, that's nitric acid, you're going to get also one hydronium, just like the HCl up here. So if we've got 5 times 10 to the negative 3, then you're going to have 5 times 10 to the negative 3 of these. And how much is going to be, what's the concentration of the hydroxide? It's going to be 10 to the negative 14 divided by 5 times 10 to the negative 3. And you do that calculation. Okay? Here's calcium hydroxide. This is a strong base, if you just look at the list. Now in this case, let's make sure we get this right. This is going to dissociate into ions. You see how I put a 2 here? I had to balance it. So this means for every one calcium hydroxide, you're going to get double the hydroxide ions. This is a 1 to 2 ratio. So if you've got 0.01, if this is 0.01, this is going to be 2 times that. 0.02. Now you've got this 0.02, and then to find the hydronium, you take 10 to the negative 14 and divide by 0.02. Okay? These were able to be calculated because you know that 10 to the negative 14 is equal to, that's the constant for the product of your hydronium ion concentration and your hydroxide ion concentration in an aqueous solution. Okay? All right, let's look at finding pH. And as I mentioned before, pH is the negative log of the hydronium ion concentration. Okay? So, here I am given the concentration of the acid, but this is a strong acid. So remember up here, For every one HCl, I'm going to get one hydronium. So if I've got 10 to the negative 2 HCl, I'm going to have 10 to the negative 2 for my concentration of hydronium. And I'm going to take the negative log of that. So on your calculator, let's see if I have a calculator here, I would do 10, and 10 to the certain power is the inverse of log. So here I have a log button, so I want to do inverse, or maybe on your calculator it says second function. Okay, notice when I hit inverse, the log turns to 10 to the x. So I want 10 to the x. I'm going to do 10 to the negative 2, but I'm going to take the negative log of that. Okay? So I want, let's do this actually. Okay, we're going to do negative log of 10 to the negative 2. Just like that. Close parentheses, and that equals 2. Okay? Why? Because the log of 10 to the negative 2 is negative 2. The log of 10 to the negative 2 is negative 2. And then we're going to take the opposite of that. It's going to be a positive 2. Done. A low pH, pH below 7, means it is acidic. This is an acid right here, increasing the concentration of hydronium ions. Here, this is a base. See the OH there? This time, to find the pH, we first are going to find the POH. So over here on the side, I'm going to find the POH because I am given hydroxide ions. And for every one NaOH, I'm going to get one hydroxide. So this concentration, because this is a strong base, it completely ionizes. That is also going to be the concentration of my hydroxide. So the POH is equal to the negative log of the concentration of hydroxide, which is 10 to the negative 2. This is going to be the same answer as up here, but this is for POH. Okay? So this is going to give me the log of 10 to the negative 2 is negative 2. Then you take the opposite of that, and you get positive 2. pH then is going to be 14 minus that number, which is going to give me 12. A high pH, 7 or above, is basic. This is basic. Okay? All right, here again, you're given straight away the concentration of hydronium ions is 3.8 times 10 to the negative 3. So you want to find the pH, the negative log of what? 3.8 times 10 to the negative 3. So on your calculator, let's see if we can do this. We want the negative log of what? 3.8 times 10 to the negative 3. So 3.8 times 10 to the negative 3. 2.42, let's go. 2.42, the pH here is less than 7. This is acidic. This is acidic. Okay? Alright, now this time you are going to be given the pH value. So pH, remember pH is negative log of the concentration of the hydronium ions. But if you know the hydronium, if you know the pH, you want to find the concentration is going to be 10 to the negative pH. Because remember, look back here at your calculator. See the log button? If I do the second function of that, or the inverse function of that, it's 10 to the x. 10 to the x and log are inverse functions. So I want to find the concentration. So I'm going to do on all of these, I'm going to do the 10 to the negative pH. So 10 to the negative 11, 10 to the negative 4.23, 10 to the negative 7.65, 10 to the negative 9.48. Okay? And that's going to give you your hydronium ion concentration. Then you would do 14 minus, you would do, my apologies, you would do 10 to the negative 14 divided by the hydronium ion concentration to get the hydroxide. I'll do one of them, and then you can do the rest of them. Okay, I'll do A. So 10 to the negative 11. So I'm going to just do 10 to the negative 11. All right. 10 to the negative 11. We can just leave it as 10 to the negative 11, or 1 times 10 to the negative 11. That's a small number. It's less than 10 to the negative 7. See how this pH is high? This is going to be basic. Okay? Let's do 10 to the negative 14 divided by 10 to the negative 11. Well, 10 to the negative 14 divided by 10 to the negative 11. Here, when you have the same base, you are going to subtract these. So this is going to be negative 14 minus a negative 11. That's like adding 11. It's going to be negative 3. So this is going to give me 10 to the negative 3. This is bigger than 10 to the negative 7. So in this case, the hydronium ion concentration is greater, the hydroxide ion concentration is greater than the hydronium. So this is going to be a basic solution. This is basic here. Okay? There's several ways you know it's basic. The pH is greater than 7. The hydronium ion concentration, the hydronium ion concentration is less than the hydroxide. Okay? Just really quickly, you can do the rest of these, but if I look at these, if the pH is less than 7, this is acidic. Here, it's a little bit above 7, so this is slightly basic. Here, it again is above 7, so it is slightly basic. Okay? But you are going to take and evaluate each of these, so 10 to the negative 4.23 to find your hydronium. And we can do this here. Watch. 10 to the negative 4.23. So I'm going to change this to scientific notation. If I move this decimal point over 1, 2, 3, 4, 5, so it's 5 point, I'll go 5.88 or 5.9 times 10 to the negative 5. 5.9 times 10 to the negative 5. Okay? And then to find the hydroxide, I'm going to write it down here. I'll do 10 to the negative 14 divided by 5.9 divided by, or times 10 to the negative 5. So 10, nope, let's do this, sorry. 10 to the negative 14 divided by my 5.9 times 10 to the fifth, negative fifth. Okay? And we get 1.69. I'll go 1.7 times 10. This E here, negative 10 means times 10 to the negative 10. So 1.7 times 10 to the negative 10. Okay? Notice low pH, below 7, that's acidic. Notice this number here is greater than the hydroxide. Hydronium concentration is greater than the hydroxide. It is acidic. Okay? So you can do C and D. All right? Okay, let's look at number 12 here. A nitric acid solution, strong acid by the way, strong acid, is found to have a pH of 2.7. What is the value of the hydronium hydroxide? Well, if you know the pH and you want to find concentration, then we have to do this right here. So I'm going to take 10 to the negative 2.7. 10 to the negative 2.7. On my calculator, I'm just going to do 10 to the negative 2.7. And I get 0.00199. So I'm going to round this to 2, I'm not 2, but to 0.002. 1, 2, 3. That's negative 3 there. 1, 2, 3. So I'm going to do 2 times 10 to the negative third. Okay, this is 2 times 10 to the negative third is my concentration. The hydroxide then is going to be what? 10 to the negative 14 divided by my hydronium concentration. So I'll go 10 to the negative 14 divided by, 14 divided by my 2 times 10 to the negative third. I think I need, no, I didn't do that correctly because I should put this in parentheses. My apologies. Alright, let's try this again. 10 to the negative 14 divided by, I need parentheses here, 2 times 10 to the negative third. There. Got to make sure you put that all in parentheses, otherwise it's just going to divide by the 2 and then multiply by 10 to the negative third. I want to divide by everything 2 times 10 to the negative third. Okay, there we go. 5 times 10 to the negative 12. Okay? Alright. Okay, so now what it's asking here is, it says, what number of moles is required to prepare 5.5 liters of this solution? Well, if we want to prepare this solution, we have this concentration right here. Here's our concentration of hydronium ions. Nitric acid, how much nitric acid do we need to make this concentration of hydronium ions? Well, this concentration, this is the concentration here. This is molarity actually right here. So this is 2 times 10 to the negative 3, and that is moles per liter. And then over here it's asking, well, how many moles, x moles, would we need if we wanted 5.5 liters? Okay? Well, I'm just going to multiply both sides by 5.5. Okay? So you're going to take 2 times 10 to the negative third and multiply by 5.5. So 0.011, or if I write in scientific notation, I move the decimal point over 2 places, 1.1 times 10 to the negative 2. Okay? There you go. That many moles. Alright, and then it says, what is the mass? Okay, what is the mass of this required to make that? So here we have moles. And if we want to find mass, we have to multiply by the molar mass. So I have to find the molar mass of HNO3. Well, hydrogen is a 1. Nitrogen, if you look on the periodic table, is 14. 3 oxygens, 3 times 16. So 3 times 16 is 48, 49, 59, and 63, if I did that right, grams per mole. All right? Well, we have 1.1 times 10 to the negative 2 moles, so we're going to take 63 times 1.1 times 10 to the negative 2, and that's going to give you the mass. You can do that calculation. Okay? All right. We are not going to do E right now. Okay? We can skip that one. Don't have to worry about that. All right. Let's look at 13, and again we're mixing in some stoichiometry and some molar mass along with this because you can never forget that. Okay. Okay, we're going to continue here. Actually, we are not going to do 13. It talks about titrations, and we just didn't get to that at this time. Let's look at number 14. See if we can do this one. It says, suppose 15 milliliters of 2.50 times 10 to the negative 2 molar, that's concentration, aqueous H2SO4 is required to neutralize that solution of KOH. Again, this is a titration. Titration is when we combine acids and bases and find out how much it takes of either or both of them in order to try to neutralize the other one or have a certain pH level. So we didn't get to that. We're not going to do that one as well. 15, we can cross that one out. So that concludes basically chapter 15. What you have to be able to do, and I'm just going to remind you this. Let me find a little space here. You have to be able to, this is not related to number 15 here, okay? You have to be able to go from pH to pOH to concentration of hydronium ion to concentration of hydroxide ions. Okay, you have to be able to move between these 4 values. Let me just remind you, I suggest you write this in your notes right now so you know exactly what to do, what calculation you need to do in order to go between these 4 values. If you and I'll show you what the relationships are that I'm using. pH plus pOH always is going to equal 14 in an aqueous solution. The hydronium ion concentration times the hydroxide ion concentration is always going to equal that constant value of 10 to the negative 14. And then pH is the negative log of the concentration of hydronium ions, and pOH is the negative log of the concentration of hydroxide ions. Those 4 relationships help me get to any of these values if I just know one of them. Okay? So if you want to go between pH and pOH, all you have to do is know that they have to add up to 14. So if I want to go from pH to pOH, I take 14 minus the pH, and that gives me the pOH. Going back the other way, I'm going to take 14 minus pOH to give me pH. Between the concentrations, all I have to do is take 10 to the negative 14 and divide by the one that I know in order to get the other one. Here, going the other direction, I would take 10 to the negative 14 and divide by the concentration of hydroxide. Okay? Now between the pH and the hydronium concentration and pOH and the hydroxide concentration, I use the definition of those, which is involving log. So if you know the concentration, to go to pOH, how do you find pOH? You do the negative log of the concentration of hydroxide to get the pH. If you know the concentration of hydronium, to get pH, you do the negative log of that concentration. To go the other way, remember on our calculators I showed you right here that the inverse function of log is 10 to the x, right there. So 10 to the x means if I know pH and I want to find the concentration, I do 10 to the negative pH. Remember, it's a negative log over here, so it's 10 to the negative pH. If I know pOH and I want to get to the concentration of hydroxide, I do 10 to the negative pOH. Okay? That right there you have to have in your notes so you can use it. You want to be able to use this right there, and now you can go between any of those values, just do the calculation that is expressed to get you from one to the other. All right? There are going to be problems like, for example, if I give you the pH and you got to get all the way over here to the concentration of hydroxide, well, you're going to have to go to pOH by taking 14 minus the pH and then do 10 to the negative pOH in order to get this concentration. Okay? All right, I hope that's helpful. As always, just shoot me some questions and let me know if you have anything that I can help you with. All right, keep up the great work.